Okay, so in this video I'm going to talk you through solving logarithmic equations and exponential equations. We're going to use what we learned in 5.5 to kind of put them together to actually solve equations. So first, to solve, if we have a logarithmic equation such as this, log base 3 of 4 is equal to 2 times log base 3 of x. Now, hopefully from 5.5 we have the knowledge that we need to solve a logarithmic equation. So looking at this equation, do you see that we have two log base 3 terms? So that's good. We can combine two logs with the same base. So in looking at this expression though, I see that, remember from the power rule, we can take this 2 and make it an exponent. So if we rewrite this expression as log base 3 of 4 is equal to log base 3 of x squared, now do you see that we have log base 3 of 4 is equal to log base 3 of x squared? So we're doing the same thing to 4 that we're doing to x squared. Do you see that we have both of them we're taking the log base 3 of both of those terms? So since the logs are the same and they're set equal to each other, wouldn't you say that their arguments have to be the same? 4 must be equal to x squared. So whenever you have a log equal to a log and they have the same base, you can take their arguments out and just set their arguments equal to each other. So 4 equals x squared, so x has to be positive 2 or negative 2. Okay, so this brings us to a very, very important rule. Do you remember from before that you can't take the log of a negative number? So we have to be very careful here. Whenever you solve your equation, you need to go back and see in the original problem, if you plug those two answers back into the original problem, do you see if we plug negative 2 in to 2 log base 3 of x, we'd be taking the log of a negative number? For that reason, that means x can only be positive 2. That means x equals negative 2 is called an extraneous solution. That means, yes, you get x equals negative 2 when you solve the problem, but if you plug negative 2 back in to the original problem, it doesn't work. So it's not a real solution. Okay, so this brings us to a problem that looks like this. Log base 2 of x plus 2 plus log base 2 of 1 minus x equals 1. So in order to solve this logarithmic equation, again, we have two logs with the same base, so that's lucky. We can combine those logs, we can set them equal to each other, we can really do whatever we want with them because they have the same base. So if we use the product rule, do you see that we can consolidate this? We can make this into one log as writing this as log base 2 of x plus 2, 1 minus x, equal to 1. And if we can get this down to one logarithm, then now do you see that this is just a log equal to a number? And we can convert to exponential. So to convert this to exponential, we say the base of the log is the base of your exponent, 2 to the 1, because whatever it's set equal to is your exponent, is equal to x plus 2, 1 minus x. Now we've gotten rid of all logarithms, we've gotten rid of all exponents or variables in the exponent, so now we have a simple algebraic problem to solve. So we say 2 equals, x, if we FOIL this out, we get minus x squared plus 2 minus 2x. And then the 2's cancel, so we get 0 equals negative x minus x squared. So 0 equals, if we factor an x out, we get negative 1 minus x. Set each term equal to 0. So 0 equals x, and 0 equals negative 1 minus x. So x equals 0, and x equals negative 1. So now, remember, we have to look for extraneous solutions. If we plug x equals 0 back in, so you basically want to plug each value back in to the original problem and see if it requires that you take the log of a negative number. So if we say 0 plus 2 is going to be positive, 1 minus 0 is going to be positive. So x equals 0 checks out. Now negative 1. Negative 1 plus 2 is positive. 1 minus negative 1 is going to be 1 plus 1, which again is positive. So we get x equals 0 and negative 1 are both valid solutions. Okay, so this brings us to solving exponential equations, which we use the same method and process in solving exponential equations that we do with logarithmic equations. If we have an exponential equation such as 5 times 2 to the x equals 3, we're going to use logarithms just like we used logarithms to solve logarithmic equations. First thing you want to do anytime you have an exponential equation is to get that exponent by itself. So in this case, we want to divide that 5 out. So we have 2 to the x equals 3 over 5. Once you have the exponent by itself, what you can do is you can use that power rule. Remember, whenever you're taking the log of a number, when you take the log of a number, that exponent you can move down and make it a coefficient. And the frustrating thing about this expression or this equation here is that we have our variable in the exponent. So if we take the log of both sides, then we're not changing the equation. Remember, you can't take the log of one side without taking the log of the other. So we're going to say log 2 to the x equals log 3/5. And since we've taken the log of both sides, then we're good. Now that we've got the log of 2 to the x, now this x can come down. This can be x log 2 equals log 3/5. And now that we've got the x down as a coefficient, do you see that we just divide log 2 out? And we get x is equal to, it's not approximately, x is exactly equal to log 3/5 over log 2. And that's about as simplified, or that is as simplified as you're going to really get without using decimals. You could plug this into your calculator and get a decimal approximation. I'm more interested in the fact that you see that this is about as simplified as you can get. Do you see that log 3/5 over log 2 is not the same thing as, I think some of you are probably thinking about the rule, log A over B is equal to log A minus log B. Do you see that this is log A divided by log B, not log A over B? So you can't, there's nothing you can do to simplify this. So this would be what x is. Another thing to note, do you see that in your answer here, if you plug this value back into the original problem, is there anything that you can't take and you can't make as an exponent? Or, yeah, there's no value that you cannot make as an exponent. So when you're solving exponential equations, there's no need to check for extraneous solutions. A lot of times people will extraneous solutions. A lot of times people will say that a value is extraneous because you get a negative number. Well, if it's in an exponential equation, it doesn't matter. You can raise a number to a negative power. It's just you can't take the log of a negative number. So I hope this helps with your prep quiz, and I will see you in class.